Now, this looks like differential equations. That's because it was, because I haven't erased the slide yet.
Turn on your projector.
Yeah.
Let's see. We ended off, we saw him, we're on the example 5.
Page, we finished example 5, I think, didn't we? Yeah, I think we did.
Yeah, looks like we did. So
5E, right.
example 6.
So we're starting page 45, systems of linear equations. You've heard all the announcements. I won't go through those again. Thank you so much. Right. Okay. One practical application for matrix multiplication is representing a system of linear equations. Well, you've got it. I'm not going to write all this down. Notice there when you put your coefficients as if they were components in the matrix. Why not? You can name them anything we want to. A11x1 plus A12x2 plus A13x 3 is equal to B1. A21x1 plus A22, yeah, all like this. Then you can write that as a matrix equation. AX is equal to B. Okay?
So does that make it kind of like a, is it separating kind of like the equal sign, or?
No, the equal sign's still right where it is. It's just rather than writing the coefficients with the variables, just do the coefficients as a matrix, the variables as a column column vector or column matrix, and that's equal to your constants, which are a column matrix.
So the
or
A would be just the numbers like we do or have been doing.
Just exactly the same.
The first column would be like X, Y, Z, right?
The first column, well, you see, yeah.
The X column.
Yeah, the X column would be, if it's a 3-variable X, Y, Z,
and then
they call it,
B would be the answer for each of those.
The answer for each of them, exactly.
Make sure I'm getting
Right.
this.
So it says solve the matrix equation AX is equal to 0. So this is just like this, only now we're going to have it 0. Now this happens to be the 0 vector, or the 0 column equation, a column 0 column matrix or column vector, but it's not the number 0, okay? Where A is equal to this set of coefficients, 1, negative 2, 1, 2, 3, negative 2, and your X vector is your X1, X2, X3, they're calling it. You could call it X, Y, Z, whatever you want to call it. And your 0 vector here is a 2-dimensional column vector, 0, 0. Okay? Now.
So we're going to multiply A by X?
Yeah, that's what you effectively are doing. A 2 by 3 by 3 by 1 is going to be a 2 by 1. That's why they turn out these sizes. Oops, I forgot to put the 0 vector. Because I can't write in bold, so I have to put a symbol over it. Okay? Now, how would we go about solving? If you wrote that then as, they're going to turn around and write it back as a system of equations, and then turn around and extract out the coefficient matrix and
pass on rewriting it a bunch of times.
say again?
I said I'm just going to pass on rewriting
Exactly.
it a bunch of times.
And then just write it as the augmented matrix, 1, negative 2, 1, 0, because that's where the constants go, and 2, 3, negative 2, 0. Okay?
I like it. It's nice.
Yeah. Now, to start with, a system of 2 equations, 3 unknowns, you know that's going to be either no solution or infinite number of solutions. You cannot have a unique solution with that. You don't have enough equations to match a number of unknowns. Now, it could have no solution. Well, this will have one solution, because this is a homogeneous system of equations. So one solution is going to be 0, 0, 0. That certainly satisfies. If x1 is 0, x2 is 0, x3 is 0, that satisfies the thing. So we know we'll have at least one solution. So therefore, this one's got to have an infinite number of solutions. Got to be infinite. Okay? No solution is not an option here because it's homogeneous. So let's proceed. What would be your first step?
Alright, so we got a 1 in the top left.
Yeah, that's what we want.
So we want a 0 below.
Yeah. How do you get that? Make that happen?
Negative row 1 plus row 2.
Negative 2, row 1.
Oh, yeah. Sorry.
That's the new row 2. Okay? So this becomes, you're leaving the top row alone, 1, negative 2, 1, 0. The new bottom equation becomes 0.
1.
Yeah, wait. That was 7. If that is a 3, I think it is, it's negative 2 times negative 2, that'd be positive 4 plus 3 is 7.
Yeah,
Okay?
I missed the minus sign.
All right. Next.
Negative 4.
Yep, negative 4
And then 0.
and 0. Yeah, I could have done that one. Okay? Now, a little messy, but what you got to do next?
Get a 1.
Where the 7 is. How do you make that happen? Unfortunately, yeah.
Well, you could do,
Yeah. Nope. Divide everything by 7.
Because you can't do anything to add row 1 row 2. Mess up your 0.
Nope. Yeah, it would mess up your 0. Absolutely. All right. So this now becomes, I just did it, row 2 divided by 7 is the new row 2. If you want to put the documentation, there it is. 1, negative 2, 1, 0, I can't talk, 0, 1, negative 4/7, one of my favorite numbers of all times, and 0. Okay?
That's really what my favorite.
Right. Next.
You gotta get a 0 above the 1.
Right?
So we're gonna do row 2 row 2 plus row
2 row 2 plus row 1 is the new row 1. Okay? Okay. So,
my favorite number.
yeah, I think what I'm going to do, well, we may have room down here. The new matrix will now be, we're using the bottom row, 0, 1, negative 4/7, 0. The pen doesn't write, and then I write again, and it double writes. Okay, new row 1 becomes, huh? 1, 0, better be, that's why we did it.
Negative 8/7 plus 1.
Which is 7/7, right?
So negative 1/7.
Negative 1/7,
And then 0.
and a 0.
Not only zeros right
Yeah.
there, this would be really
All right. So now, what is our solution? I want to say family of solutions, but that was in,
Oh yeah, because we can't really do anything else to this.
no, can't do a thing else. So you let x3 equals some parameter. Their favorite is t. It could be s, r, whatever you wanted to name it. Just not x, not a, not b, you know. Do something else. Okay. But then your x1 is equal to is equal to 1/7 t, or t over 7. I put it on the other side.
Yeah.
Right. And x2 is equal to 4t over 7. And x3, course, is equal to t, because that's where we chose it. Okay.
And that's as close as we can get to an answer.
No, there's several more. In fact, one that's a lot cleaner in my mind would be let x1 equal t, or pick another one if you want to, x2 equal 4t, and x3 equals 7t. That'll do the same thing, but just without any fractions in it, right? Because of course 0, 0, 0 fits on all of them, but if you let this t be 1, then you have 1, 7, 4, 7, 1. This would give you 1, 4, 7, which basically I'd rather have that order triplet than a bunch of fractions. Okay? And that way, but to get 1/7, let t be equal 1/7, that would be 4/7, that would be 1. So you get right back to 1 you had before. So, yeah. It doesn't matter which, that to me is the cleanest. But what did they do? Yep, they did x1 equal t, 2 equal 4t, x3 equals 7t.
7.
Huh?
70.
7t, yeah. Okay. 70. Yeah. All right.
Too bad Victor wasn't here to enjoy that.
What's that?
I said too bad Victor wasn't here
Oh.
to enjoy that.
Right. Okay, so, and then any multiple of that, fractional multiple, any kind of multiple will work. I have a little blurb here on technology, online technology guide available at cengagebrain.com. I don't know if you want to use that or not. I don't know. I've never used it, so I can't tell you whether that would be beneficial or not. Now, believe it or not, we've been using partitioned matrix. We were calling them augmented matrices before. They're basically almost the same thing. No, they're not. They're sort of going in a different direction.
Basically cutting up your matrix and multiplying it by whatever variable.
Right. It is, yeah, breaking the matrix into columns or rows, and doing things. So your x1 is times your first column, your x2 times your, let's see, it's not, yeah, plus x2 times the second column plus x3 times the third column equal b. Same thing as if you wrote the whole thing. You just partition it. So that then is called the linear combination of the column matrices, and the coefficients are then it sort of turns things on their head. It sort of treats the variable as a coefficient, and the column matrices, they're not variables, but that's what you call them. Huh?
It's coefficients multiplied by the variable.
Yeah, exactly. So.
You could think of it as kind of like factoring it out.
Yeah, exactly. So linear combination of column vectors of the matrix product AX is a linear combination of the column vectors A1, A2, A3, up to AN. When you have n variables, then x of 1 is times the first column, which is your A11, A12, down to A11, A21, A21, down to AM1, x2 times A12, 13, 22, 2M2, I keep saying them backwards, plus x of n times 1n, A 2n, A down to mn. Okay. To me, yeah, fine, y, okay. Furthermore, the system AX plus B, matrix A, column vector X equal column vector B, is consistent if and only if B can be expressed as such a linear combination where the coefficients of the linear combination are a solution to the system, where the coefficients are now your variables. Okay, yeah, sort of crazy. Let's do example 7. Okay, so let's clear all this out of the way, and we'll do that kind of thing we were just talking about. Here is your linear system. x1 plus 2x2 plus 3x3 equals 0. 4x1, they're very, very creative in their coefficients here, plus 5x2 plus 6x3 is equal to 3. 7, I'm guessing it is x1 plus 8x2 plus 9x3 is equal to 6. Yeah, I thought that was going to be the case. So, the way they were just describing, for some reason they want to do it, is x1 times the column of the 147 plus x2 times the column 258 plus x3 times the column 369 is equal to the 0, 3, 6. Okay. Now, using Gaussian elimination, you can show that this system has infinitely many solutions, one of which is this. Okay? Now, Gaussian elimination, you'd have to go back to your augmented matrix and do it to get to the Gaussian elimination.
So,
you're taking their word for it now because we're not actually doing it. Is there any reason that we can look at this and say, yes, it has to be true?
well, I mean, you can look at this algebraically.
What's that?
You can assign different values to the x's to make it work.
Okay, but you have to figure out what ones to do. And you'd have to do the Gaussian elimination to get those, is what I'm saying. So,
Why did they have us do this?
well, the thing that comes to my mind is this was such a pattern in the coefficients in the solution, you almost guess they have to be dependent. But no, they would. If this would have been a 0, 4, 8, that probably, I haven't done it, but probably it would work. You know, I don't know for sure, but let's see. Is what I'm getting from you, it's not worth doing to see what this comes up to being, or do you think it is?
Why didn't they throw it in augmented matrix first? Because
Right.
You
You can't do it without. That's what I'm saying. Is they're just saying it doesn't work. So, but do you feel it's worthwhile to do the augmented matrix and work it out? Okay. My gut feeling is that too, because I don't like to take the word for anything. This produces what is the augmented matrix?
1, 2, 3, 4, 5, 6, 7, 8, 9. Or wait, I've left out the zeros. Excuse me.
Yeah, you forgot those. Okay. And fortunately, it starts with where we want it to start.
Yeah.
I'm going to see if I can squeeze them all in here. It'll be tight. What will you do first?
Well, -4 times row 1 plus row 2. And then -7 row 1
Right.
plus row 3. So, to get 30.
Okay. So we're using row 1. So 1, 2, 3, 0. That gets there. What's your new row 2?
0.
0. -3. -6. 3. Next. 0. I don't think so. -6. negative. Say again, I can't hear. Okay. 21. Yeah, negative 12. Okay. Right.
Now we got to get that negative 3 into equal 1.
Okay, and how's to do that?
Well, actually, we can divide rows. We can divide that last row by 2.
Okay. Or even better, negative 2.
Negative 2, that's what I was
Right. And then you got exactly the opposite of the row before. Add those together, you get a row of zeros. That's where your infinite number of solutions comes from. Okay? Because that will give you a row of zeros at the bottom.
So if I get half of row 3.
Well, actually, the easy thing to do is divide row 2 by, well, even easier. Multiply row 2 by negative 2 and add it to row 3, and that'll give you your zeros. Okay? Now, technically, we don't usually do that, but why not? Okay? 0, 0, 0, 0. Okay? That shows you're going to have an infinite number of solutions. But then, and write the first row, we're not using that at all. But then the second row, don't write it the way it is. Divide it by negative 3. Yeah. Okay. So that'll give you a 0, 1, 2, 1. Negative 1. Right. Okay.
And that's pretty much it.
Well,
Well,
if you want to get. Oh, did they say Gauss or Gauss? No, they said Gaussian elimination. You've done it. Done it right there. So then you can say let x3 equal, their favorite is t, and then x1, well, let's do the x2. x2 plus 2t is equal to minus 1, so it'd be x2 is equal to minus 1 minus 2t. So stupid. Okay. And then we can do x1 plus 2x2 plus 3x3 is equal to 0. And that would be x1 plus 2 times a negative 1 minus 2t plus 3 times t is equal to 0. Huh?
Oh, you plugged in. Okay.
That's right. Yeah.
You plugged in what we found for
Yeah.
x2.
Yeah. Let this variable, because this doesn't have a leading 1, let that be your parameter. They love t. And then the second equation, x2 plus 2t is minus 1, so x2 would be minus 1 minus 2t.
So it'd be x1 minus 2 minus 4t plus 3t.
Yeah, exactly. That would be the next step. x1 minus 2 minus 4t plus 3t is equal to 0. This is so stupid. Okay. And then that would be, simplifying that would be x1 minus 2 minus t is equal to 0. So x1 is equal to t plus 2.
That also.
Right. Or 2 plus t. It doesn't matter.
Okay.
And that's why they say, let's let t equal minus 1. Why, I'm not sure, but let's do. Then x1 would be 1. x2 would be 1. And x3 would be minus 1. And that's the one they chose to. Okay?
And did you choose any number
Yeah, and plug them in.
So
Yeah,
you could just do like
you could do 0. Yeah, and then, but of course, well, no, I was going to say, of course, this isn't homogeneous, but that happens to work in this case because
this
it
is
just
infinite
happens to
solution.
be there. Yeah.
So on ones that we have, it's infinite solutions. Once we
Oh, wait, I'm sorry. If t is equal to 0, then you would have, okay,
x of 3 would equal 0.
that would be 2,
To your left. Right there.
yeah, 2, -1, 0. That would- I was going to say 0, 0, 0.
And that would be your answer. So anything you plug in, once you find what, said
These
each variable
parametric
equal to
equations
t,
are, yeah. Then
you
you
just
should
plug
that
in
in.
any number for t and
Right.
find a new set of solutions. Okay.
You could put in pi thirds if you wanted to. I won't want to either. Okay, so, but it can be done.
Who wants to do that?
All right.
There's sines and cosines, maybe, but otherwise.
No. All right.
And 2.1.
We're awful close. Just as you partition A into columns and X into rows, it's often useful to consider an M by N matrix partitioned into smaller matrices. For example, the matrix 1, 2, 0, 0, 3, 4, 0, 0, -1, -2, 2, 1. You could partition into
They just sent out an email. There's a Blackboard training for students.
when
I'll have to look at the flyer.
Oh,
So
okay.
just saw it come up. So
Yeah.
you might want to check your inbox. You may have to do an announcement for
Yeah.
students.
tomorrow, well, Monday's class. This is it for today for me. So
Yeah.
So you can set these just all sorts of ways. They didn't say what to do with that first partition they did, where they did a 2 by 2, a 2 by 2, and a 1 by 2, and a 1 by 2. How you could use that, but certainly it looks like if you make that 0 matrix its own partition, that might give you some benefits. I can't see why. Or you can split it into column vectors, and each column, C1, C2, C3, and C4 are columns, or partition it by rows and have R1, R2, and R3 being your rows. Now, again, yeah, you can do it, but what's the point,
Is this going to be useful in any situation?
I'm sure it must be, but I can't think what it is, so we'll get there and see. Yeah. Linear algebra applied, when they're talking about things like flight crew scheduling for any airlines, they just used American here. Is that still in existence? I think it is.
American
Isn't it?
Airlines?
Yeah. But they merged with somebody, but they kept the name American. Okay. Require manipulation of 837 rows with more than 12,750,000 columns, and that application of linear programming required that the problem be partitioned into smaller pieces and then solved on a Cray supercomputer. Okay, if that's of interest to you, they give one article here that you could do that with. Okay, pretty incredible.
For scheduling.
Right.
Like,
No wonder they get these guys with all screwed up. No, I didn't say that. But,
12
all these
billion columns.
yeah, and that's where then certainly partitioning should help somehow, and they're suggesting it can.
837 rows.
Yeah.
I'm just trying to wonder. So is that like 837 aircraft, and then there's 12 million plus different shift opportunities?
Yeah, and maybe that's the permutation of all those. I would think they keep a crew together, but maybe not. I don't know. But if you think about it, a crew might be able to go.
Crew lives somewhere.
Uh,
They have to get together, and then they go this place, and then they have to make some kind of flight somewhere else or back.
right.
So
And
that adds to the 12 million.
right. But if you think about it this way too, Atlanta to Birmingham, that crew could then turn around and do Birmingham to Atlanta. It could probably do bunches of flights in a day. But Atlanta to Los Angeles,
Probably
Yeah, because by the time you fly back, I think your whole day would have been, in fact, you've exceeded your hours. So you might be able to do one or two short hops after that. So you see, there's all kinds of permutations there that you do. Because the constraints are the crews can't, especially the pilots, can't fly but so many hours in a given so many hours, you know.
Do a flight from Los Angeles to the East Coast.
Yeah.
Late in the evening, a red-eye flight, or
yeah.
whatever, basically you lose all of the night.
Right.
It's gone.
Yeah.
In the evening, you get there in the morning.
Yeah. So you better have had so many hours sleep before that, you know, and stuff. So, yeah, it can really get to be sort of hairy. And like you say, that finishes 2.1 and homework exercises. And let me just check. I think this one has all of them in the back, isn't it? It looks like it.
I think I want to say the actual flight takes somewhere around 4 hours to actually do this.
Yeah.
You lose 4 more hours, so it's an 8-hour flight.
Right.
It's crazy, you know?
Okay, you mean for time zones, you mean? Or, yeah, right.
Time zones. And then, like, if you actually take a timer, it's going to take about, I want to say 4 hours. I'm not sure if that's right.
Yeah.
You just basically double it.
Right. Well, but going the other way is a 1-hour flight or something like that.
Or, same time.
Same time, yeah.
We get on the plane at 10:30, we get off the plane.
Yeah.
Yeah.
Actually, Birmingham to Atlanta quite often is that way. It's either 2 hours or no hours. Right? All right. Homework exercises, either 1 or 3. Have
we checked and seen how the exercises in this book are?
Yeah, that's what I was just checking. I think they have them all. I thought I had checked that before.
I'll check.
Okay, yeah, check for the student edition.
1 through, we have to, 87.
Yeah.
I feel like that's going to be everything.
Yeah.
Yep.
So either 1 or 3, any of the odds 5 through 11, either 13 or 15, any of the odds 17 to 29, any of the odds 31 to 37, do 39, any of the odds 41 through 47, either 49 or 51, or both if you choose, 53, 55, 57, and by the way, 57 is introducing a new definition. And if you look for it anywhere in the text, you'll never see it defined. This is where it's defined, what they call a diagonal matrix, which has numbers on the diagonal and zeros everywhere else.
So it's kind of like reduced row echelon form.
Yeah, when you finally get to it, except reduced row echelon form, you could skip a column or have some spare at the end. Diagonal matrix has to be square, and they all, your ones have to be, except this doesn't require them to be ones. Reduced row echelon could have to be ones, first non-zero entry of 1, but this has to be, these can be any numbers. So that's what a diagonal matrix is.
They can skip stairs.
Yeah. So do 57, 59, 50 or 61 if you choose. It's a guided proof. Either 63 or 65. 67 again is a proof, so that's up to you. Either 69 or 71. In 73, we kind of cheat a little bit and get into complex numbers. So if you want to look at that, you certainly can. 75 is a proof. Any of the odds 77 through 79, no, through, goodness. Let's make it through 81. Choose the ones that are greatest interest to you or closest to your major or interest or whatever. Of course, your major they're all close to. Okay, 83, and then 85 is just a true-false, and then 87 is actually a workable one. Okay, let's move on to 2.2. How are we doing on time? We talked a bit and stuff.
About 11:45.
Okay, we got 30 minutes.
We're going to run down the hall right now.
Okay, I'll go on and keep talking. Okay. 2.2, properties of matrix operations. We're talking here about the algebra of matrices, okay? And we've already hit some of this before. This is going to sort of tie it together. 2.1, we concentrated on the mechanics of three basic operations: matrix addition, scalar multiplication, and matrix multiplication. But now we're going to talk about how these things combine and what are some general rules for this. So here's theorem 2.1, has 6 steps to it. And since maybe not everybody has books, let me erase all ink on the slide. Okay. What we have, A, B, and C are matrices. They all happen to be the same size, M by N. M rows, N columns. Okay? C and D, scalars. Okay? Any real numbers. And with that given, the following properties are true. Okay, now remember these are same size matrices. 1, A plus B, 2 M by N matrices, exactly the same as B plus A. So addition is commutative. Addition of matrices is commutative. Commutative property of addition of matrices. Okay? 2, if you're adding, started trying to get it the same way they do. A plus B plus C is the same as A plus B grouped together plus C. Okay? Now this is only true, of course, if they are the same size. That was given. They are all M by N matrices. So yes.
Basically, it doesn't matter what order you have.
What's that?
It doesn't matter what order you have.
Exactly. That's it. As long as they're the same size, that's certainly true. So this is the associative property of matrix addition. This is a commutative property. This is associative property. Okay, the third one. This is a little strange, but true. I mean, why would you even question it? It seems like to me. If you had the two scalars, multiply them together and multiply that by matrix A, that's the same as multiplying the first by the product of dA. In a very weak sense, this is the associative property of matrix.
Basically, it's just for scalars.
Yeah, associative property of matrix scalar multiplication. Now they just call it matrix, or they just say associative property of multiplication. You can't say that for if those are three matrices. You couldn't even multiply those three matrices together unless M was equal to N. Okay, so I want to say matrix scalar multiplication, not just multiplication. Okay. Now, 4, this is always true. 1 times A is A. Okay, that's the identity element. Multiplicative identity. Okay, number 5. C times A plus B is equal to CA plus CB. That was my uncle's name. Okay. And that is a type of a distributive property of scalar multiplication over matrix addition. Now they don't do that, they just say distributive property, okay? but scalar multiplication over matrix addition. Number 6 then is kind of the reverse of it. They put the scalars in front. C plus D times A is equal to CA plus DA, which is kind of distributive property of matrix multiplication over scalar addition. Okay. They just say distributive property again, which to me is a little on the weak side. Okay. They do show a proof, and since you may have turned out being a math major, this may be something of interest to you to do, but that shows you how you go about proving some of these things. You let the matrices be represented in the subscript notation. Okay, so and show that those are then always true. All right. The preceding section defined matrix addition as the sum of two matrices, making it a binary operation. The associative property of matrix addition allows you to write expressions such as A plus B plus C as A plus B added to C, or A plus B plus C added together first. Same reasoning applies if you have 4 or more matrices. This happens to have 5. Example 1 here. Let's go to a clean. To obtain the sum of 4 matrices, they have to be the same size. Oh no, 4. Add the corresponding entries as shown, and it's pretty simple. 1, 2 plus -1, -1 plus 0, 1 plus 2, -3. Okay, what would that be equal to? Add all the corresponding elements. 1 plus -1 is 0, plus 0 is 0, plus 2 is 2. 2 minus 1 is 1, plus 1 is 2, minus 3 is -1. Pretty simple to do. All right. One important property of the addition of real numbers, that is that the number 0 is the additive identity element. They showed here on the previous slide the multiplicative identity element. Okay, 1 times A is A. Okay.
0 plus A.
Okay, except that now you have to be talking about a 0 matrix. If A is a matrix, you have to refer to the 0 matrix. And that 0 matrix must be the same size as your A matrix was in order to add them. So then you can extend 2 more here. So now we have A being, this is theorem 2.2, an M by N matrix, C a scalar. Okay. Then the following properties are true. A plus the 0 matrix M by N. Now they just do MN, which is fine. I guess that's okay. I prefer M by N because that's real clear what you're talking about. But MN, I guess, is okay. And that's equal to A. Of course, if A is an M by N, the 0 matrix has to be an M by N as well. Otherwise, you can't add them. And what's more, number 2, if you add A to exactly the opposite of A, every element is the opposite of the corresponding element, that's going to give you the 0, and of course, negative A is also M by N. That gives you the 0 matrix that is M by N. They call it MN. Okay? And then the third, dealing with zeros here. If C times A, they left off the parentheses, it doesn't matter, is equal to the 0 matrix, M by N matrix, then that implies that either C is equal to 0 or A is also the M by N 0 matrix. Okay. Hunger is setting in. It's never far. Okay. The algebra of real numbers, algebra of matrices have many similarities. You can do a lot of the same things with it as in solving equations. Just remember this. Matrix multiplication doesn't work the same way as regular multiplication. So be very careful of that. Scalar multiplication, no sweat. But matrix multiplication, yeah, sweat. Okay. So let's go to example 2. My goodness. I'm getting so hungry. Solve for x in this matrix equation. 3x plus a is equal to b. X being capitalized like that is a matrix, not just a variable. Where a is 1, negative 2, 0, 3. And b is, better also be a 2 by 2, negative 3, 4. 2, 1. Say again?
Subtract A over to the other side.
Yes, you got it.
And then multiply by 1/3.
Right. So that.
I would say that for after we end.
What's that?
I would say that for after we end.
Yeah. You do the 1/3 afterwards. Or you could divide everything by 3. That would be x plus 1/3 a plus 1/3 b is equal to 1/3 b. Then subtract 1/3 a from 1/3 b. But it's, I think, easier to subtract and then do. So this would be 3x is equal to b minus a would be what?
B minus A. So let's just flip the signs and then add them. Right?
What's that?
Flip the signs and add.
Yes, exactly.
So -1, 2, 0, negative 0.
Okay. What's your first entry? Oh, okay. You were just changing the sign. Got it. Okay. Okay.
So rewriting. Alright. So that'd be negative 4.
Got it.
6.
Got it.
2.
Got it.
Negative 2.
Negative 2. Got it. Okay. What would be your x then?
1/3 of that. Right?
1/3 of that whole thing. Negative 4, 6, 2, negative 2. Or if you wanted to actually multiply it through, that would be negative 4/3, 2, 2/3, minus 2/3. I don't know how the book left it. Let's see. Yeah, negative 4/3 to 2/3, negative 2/3. Got it. All right. Then when we get to matrix multiplication, you got to be kind of careful. Okay. Note that there's no commutative property of matrix multiplication. Okay. Although the product AB is defined, the product BA may not be defined. Okay. And certainly, even if it is, there's a good chance it's a different size matrix, which then couldn't be equal. Okay. So, for instance, if A is a 2 by 3 and B is a 3 by 3, you can multiply those together. That's clogging up. Okay. So if A was 2 by 3 and B was 3 by 3, AB is defined. What size would that be?
Say the sizes again.
Okay, A is 2 by 3, B is 3 by 3. AB, it would be a 2 by 3. Would BA be defined? Would BA be defined? The product.
Where are we at?
Okay, that remark at top upper left of the page.
Oh, okay.
Yeah.
No, it wouldn't be defined because it'd be.
Yeah, BA would then be a 3 by 3 by 2 by 3. The middle ones don't match. Can't even do it. Can't even do it. Okay. But even when you can, that still doesn't guarantee it wouldn't be commutativity. But let's see what Theorem 2.3 does say. Let's get out of here. Literally. No. A, B, and C are matrices. Okay. Notice they don't give a size. They say with the sizes such that the given matrix products are defined. Sizes.
Basically, so they work.
Yeah, sizes will work. I'll put it that way. Okay?
So this
Short
is really the law of the land.
Right. C is a scalar. That doesn't matter what size scalar it is. Any old scalar will do. Any real number.
But if these were all square matrices, then it'd be kosher.
As long as the same size square matrices.
Yeah.
Yeah. Okay?
3 by 3, 3 by 3, 3.
Yeah, exactly. Okay? So number one. A times BC is going to equal AB times C. We don't have to be quite as constrictive as being squared. Certainly it'll work if they're squared. But even if A were and say an M by N, B would then have to be an N by, say, P, and C would have to be a P by anything. That could be Q. Okay? Then when you multiply these together, you're going to get an N by Q. Multiply that by that, you'll get an M by Q. Okay? Well, up here, this would be a M by, no, the product would be M by N times, okay, I'll write it out. M by N, N by P, P by Q. Okay? I'll write it shorthand. Then these two multiply, and that'll be an M by P. And then these two will multiply and be an MQ. So sure enough, they're the same sizes. And the numbers will work too. Okay? So as long as they're compatible sizes, they don't have to be the same square matrices, but as long as they are. Now, let's look at the second. Okay? This is the A times B plus C. Now in this case, B and C have to be the same size. Okay? So let's say A is an M by N. This will be an N by P. This also has to be an N by P. Okay?
They have to be the same size?
To add them, they have to be. Yeah. And so this will result in an N by P, and then these will multiply to be an M by P. Okay? Now, this makes no sense. Okay? I guess if I tap on the screen, it turns off. That may be it.
If you tap on it, it may receive it as a click.
Yeah. Okay? And the rule says then this is an AB plus AC. Okay? Well, let's see if the sizes will work. Certainly they will. M by N, NP, MN, NP. So sure enough, this will be an MP, MP, and those who add to be an MP. So yeah, military police, that works.
I was thinking the same thing.
Okay.
Got a whole police.
Yeah. And then the third one, and the numbers will work too. Let's see if we can get the third one written in here. A plus B times C. So this would have to be a M by N, M by N. To add them, they have to be the same. This would have to be a N by P, okay? Then this would be A C plus plus BC. Sorry about that. And this would be a M N N P, M N N P.
Sounds like a cheap knockoff band.
What's that?
Sounds like a cheap knockoff band.
Yeah, right. And those add to be a M P. Okay, so yeah, at least the sizes work, but also the numbers will work too.
And I mean, some of this, you'll kind of see it as you go along.
Yeah,
More
exactly.
so than like,
yeah.
You'll be using it and figure out, oh, this doesn't work if you try to do that.
Yeah. Now, what you can't do though is reverse an order. Okay. A times BC certainly cannot be the same as A times CD.
Yeah.
It can't happen.
Or B times AC.
Yeah, exactly. You can't screw with the order at all. Okay. Even here, AB, you can't change this to be a BA or a CA. No, you can't do that. If you put the A over here, then it does do okay that way. Okay, and that's what that's saying too. But you have to do them in the same order, otherwise you'll generally get totally different numbers. Okay, and sometimes the sizes won't match either. Okay, and number 4 is probably the simplest because it's dealing with scalar. C times AB. Okay. Yeah. It's CA times B. And that's also equal to, where did they put it? Yeah, A times CB.
Okay, no, they don't screw with the order. They just put the
Okay.
constant.
Yeah, that's a scalar. Scalar can move around. Matrices cannot. Yeah. Exactly. Those are all equivalent. Okay, and if you want to do the proof, which is not a bad idea for you since you are a math major, you'll probably be doing a bunch of proofs in your future. Okay. Find the matrix product ABC by grouping the factors first, then that, and show that you get the same result. So let's do we have enough time for this?
We got 9 minutes.
9 minutes, I think we may. Here's A. 1, -2, 2, -1. Here's B. 1, 0, 2. 3, -2, 1. And here's C. -1, 0. 3, 1. 2, 4. Okay. Got it. Now, what we want to do first is AB times C. Okay? First question, can you even do that? Can you do AB?
Yes.
2, 2, 2, 3, that's going to give you a 2, 3. Then you can multiply that by 3, 2, no problem. Okay, so that will work. So what do you get when you multiply A times B?
This is what I need a little bit of practice on. So, first lot is...
Okay, what's the size of it now? I said it before. 2 by 3. I like sort of to put those in, make sure I fill in all the blanks, okay?
So, the row of A times the column of B would be the first blank, right?
Right. Row 1 times column 1, right.
Then the second
So let's,
row of A times column 2 of B will give you the second.
Okay. Let's just do one. Which one you want to do first?
I'm just trying to understand how it plays out.
Okay.
Just
All right.
make sure that I understand.
This is the 1-1 entry. So do row 1 there, column 1.
Okay, so if you think about it as like a first entry, second entry, like an X, Y, or
Right.
it'd be A, B for each of them, right?
Yeah.
You gotta go by the row of this one, the column. of
Column,
this
yeah,
one. Okay.
yeah. But when you're doing that, do IJ. X, Y, you know, that may, you know, IJ is, that's the proper nomenclature for it. I being row, J being column. Yeah.
Alright, so first one
Yep.
would be 1, right? Times -6.
Yeah.
Plus -6, which would be -5.
Negative 5.
And then I guess we can go over from that and get 1 times 0, which is 0, plus 4, which is 4.
Got it? Yep.
And then 2 minus 2 is 0.
Got it.
Okay, now we're going down to the second row, back to the first column. 2 minus 3, or no, is that a negative? That
Yeah.
is positive. So it'd be 2 minus 3, which is -1.
Got it?
Then 0 plus 2, which is 2.
Yep.
And then 4 minus 1, which is 3.
Got it. Okay. Then we're going to multiply that by -1, 0, 3, 1, 2, 4. What size will this turn out being?
2 by 3 and 3 by 2, so 2 by 2.
Yep.
Alright. Okay, so for the first blank, row 1, column 1, that's 5.
Yep.
Then 12.
Yeah.
So that'd be 17 plus 0, so 17 for the first blank.
Right.
Okay. And then for the second blank, you have 0.
Yep.
4, 0, so it'd be 4.
Got it.
In the second row, first column, what is it, 1 plus 6, which is 7, plus 6, which is 13.
Got it.
And then the second column, 0 plus 2 plus 12, which is 14.
Okay. Let's see what happens if we do it the other way. A times BC. That would be, I'm not going to write, yeah, I got to write it. 1, -2, 2, -1. Now, let's see if we can do BC as is. What size will BC be?
2 by 2.
2 by 2. So I wrote it too big, but that's fine. What will that be? Looking up above and doing them, what will we get?
-1, 0,
3.
3. And then 0, 0, 8.
8.
-3, -9,
Great.
7, right?
Oh,
-6. It will, yeah, -9 and 7, right?
yeah. Oh, you're adding as you go. Okay.
7. Negative
What you get?
7.
Negative what?
7.
Okay. Yeah. Okay. All right.
0. So -2 plus 4, which is 2.
Okay.
So 3, 8, -7, 2. Right?
Yep.
So then this one will be the last one. That would be 3 plus 14, which is 17.
Got it.
I'm guessing it's 8 minus 4.
Got it?
6 plus 7 is 13.
Got it?
And 16 minus 2 is 14.
Look at that. They indeed are equal. Okay.
Alright. We proved it for them.
It wasn't proof,
No,
but
it
it does support it. Okay. All right. Have we got time for 4?
Don't think so.
Okay. What's the time?
Only got 1 minute.
1 minute. Okay. So we'll begin next time at number 4. Example 4. Put my page in there. And homework exercises here. This is a relatively long section. Any of the odds 1 through 5. Any of the odds 7 through 11. I think we did, yeah. Any of the odds, or do number 13. Any of the odds 15 through 19. Do 21. And I think the next one is like our, yeah. We'll stop there and pick up there next time. All right. So we'll call this section 2.2.